bridge regression, then we start with our basic assumption of regression. Examples should be IID, which means the columns or the features or independent variables x1, x2, x3, x4, etc. They are all independent. Why? Because our equation is that y hat will be equal to w naught x naught plus w1 x1 plus w2 x2 and so on. And this model is linear combination of weights and inputs. If inputs are not independent, then we need to include a term like term z that works with x1 and x2 interacting, their correlation in some way, right? Maybe another z2 that works with x1 raised to the power x2 or whatever, right? Well, we don't want to explain those interactions. Linear combinations means main effect. So a regression model is main effects model. Individual variables. This W means the effect of individual x1 on target variable. Individual effect of independent variable on target. So once we have correlations, we cannot, basic assumption is that we are trying to make a main effects model that explains individual contribution, not going together contribution, individual. Once they have correlations, x1 and x2 are correlated, in that case, this model is not sufficient. We need to look beyond, go somewhere else. So how do we measure correlation? We can just use pairwise correlations in your inputs. Right? So what we look at is a square matrix. If there are 4 variables, it will be a 4 by 4 square matrix, and the diagonal will be self-correlation. It will be always 1. The other cells in this correlation matrix, either upper triangle or lower triangle of this matrix, you will look at, and if you see one or more pairs, so every cell reflects pairwise correlation. Pair of x4 and x3. Pair of x2 and x1, how much correlated they are. If we have extreme values between nearing -1 or +1, this is the ideal case. So IID means we want all these values near 0. Only then regression solution is valid. Regression solution is interpretable or valid and valid only if we have correlation 0. What if we don't have correlation 0? We can sense that by looking at these coefficients. These coefficients will try to reflect the correlations. So if two variables are correlated, their x1 and x2, if they are correlated, then the coefficient of x1 will show the contribution of x2 as well on y. Coefficient of x2 will also show contribution of x1 on y because they are going together, right? They are correlated. So the size W1 will be either inflated or deflated from its actual true size. The true contribution of x1 is, let's say, 1. 1 is no. 1.5. But if it is correlated with others, that 1.5 may look like 2.5. So we will interpret that y is affected 2.5 times for every unit change in x1, which is not correct. So the true coefficient we will not be able to find if these are correlated. Correlation means, in the beginning we started, the effect of violating IID or regression model. Overfitting is first inflation in the size of coefficients. We cannot avoid correlation. In real life, all data sets have correlations. What we can do is that we can formulate the estimation of weights in a way that they don't inflate. Two ways that we are going to discuss today are Ridge regression and lasso. Ridge regression lets us control this inflation or deflation in weight size. That's all there is. Now, look at this. What do you see here?
X1 and X2 are correlated.
It's a correlation matrix, and x1 and x2 are correlated, right? 0.98. What else?
X1 and 2 and Y. But it's not even.
So, for a moment, we keep this in mind that x1 and y are strongly correlated, and x2 and y are also strongly correlated. x2 and y, x1 and y. But since y is our target variable, in the beginning we don't look at that correlation. We just keep it aside, focusing on the pairwise correlation in the independent variables. This is a matter of concern. That means the coefficient for x2 and coefficient for x1 will not be true coefficients. They will not reflect independent contribution of x1 and x2. If we try to estimate the contribution of independent variables using least square coefficients, the intercept is estimated as 0.22. x1's contribution is negative. x2's contribution is 2.4. Now, we are going to learn a way such that this deflation and this inflation is controlled, not by treating the data. We don't test data yet. We are going to learn a technique where we test the data and try to decorrelate it. But what if we cannot? In that case, we can try to control this deflation and inflation in the coefficients, regression coefficients. So x2 for regular model that we have been doing till now, x2 is important as 2.42. 1 unit change in x2 changes y 2.42 times. 1 unit in change in x1 changes y negatively 0.41 times. On the other hand, we will look at the solution that is ridge regression. The coefficients will look like this, x1 and x2, which is bit justified. X1 and x2's coefficients are bit justified. Another thing that we will pay attention to is that if we standardize our data, inputs are normalized, zero-centered, standard deviation is the distribution is normal, then the coefficients are even better. Original data 0.95, ridge regression will give 0.46 if we standardize our inputs. On the other hand, the standardization effect is not limited only to ridge regression. You can also see that on least square solution, regular least square solution that we have been doing. Original data minus 0.41, standardized 0.2, 2.4, 1.2, halved. Coefficients are halved. Now look at this. Standard error is the amount of deviation. So this coefficient 2.42 can go wrong, plus or minus, as much as this amount. Very high standard error. It can be 3.42 or 1.42 within that range. The confidence interval is too wide, but in case of ridge regression, confidence interval is very narrow. More precise estimate. The effect on R squared, if you remember, R squared is the contribution of this model in explaining the variation in Y. The regular regression least square regression will look like having 99% power to explain variance in Y, which looks very cool. This means model is fitting the data very tightly, but it also reflects overfitting that you mentioned in the beginning. So model fits the data too tightly that it cannot generalize well. So on the other hand, when you apply ridge regression, your R squared value will reduce from 99% to 95%, which may seem like a disadvantage or some negative point, but actually reducing R squared from overfitting to better fitting situation. Now you want to look at, you know that in real life we have all inputs correlated. Not all, at least a couple of the inputs are correlated. In case of correlations, you see the effect, deflation, inflation, in the size of the coefficient. Standard error, it means this estimate is very poor estimate. It can go plus 1 this side, plus minus 1 this side, too wide confidence interval. What's the use of an estimate that can go this wrong? And if you apply two ways to control. One, you standardize. Standardize will reduce the size of coefficients equally for both regular least regression and standardized race regression. Both will benefit. But this effect of one variable more important than the other, we cannot control by just fixing the standardization. We need to have another way. In that way is race regression, where you can see the contribution is more justified. If standardized data, 0.46, 0.49. So every variable is having more justified coefficient. It's like in your group assignment, the score is group score, but one person contributes more than all others, then his weight should be more. But if the model is naive, it will give everybody kind of anyways. So how do we do this? We have this error, sum of squared errors. We include a penalty term in our error. We want to minimize this error as well as the size of the weights. We call this L2 norm. So we L2 norm is W is a vector. So for every X we have corresponding W. Right? So we take norm of this vector and add that to the error. That means, in other words, we are saying that if the size of weights is inflating, we consider that part of the error. Right? Lambda is a hyperparameter. The value is 1, you just have, if value is 2, that means the error is as much as the norm. If lambda is 0, that means you don't want the size of the weights to be considered as part of the error. So, if this is your error function and you want to reach here, minimize this. But adding that size of the W to the amount of error will stop you here. If you move farther, W will increase. So you need to stop at higher error. It's having a constraint. A mean function is this, but it is constrained by another function. It needs to be equal to 1, then only feasible values that you can have for X are on this side. So it's like you constrain your optimization problem of finding best values of W's. Now, if remember we have this E transpose E, our squared error in matrix notation, we write it like E vector transpose E will give us squared error. We want to differentiate it with respect to W. Changing W, how much error changes, right? So that equation that we looked at in the previous module, we used X here, original data. But let's normalize our data and refer to that normalized version as Z. We scale it, put every variable on 0 mean, and spread with how much spread it has. It will be a normal distribution. So if we refer to that as Z, multiplied by W, your Z matrix input variables, multiplied by vector W, minus target T squared. This is your error. Not squared, transposed. ZEW minus T. So when you solve this, you get E transpose E, sum of squared errors. But now, for ridge regression, you are also including this term, W transpose W, which is L2 norm. L2 norm of this W vector is squaring those values, squaring these values and summing all. So you can get that using W transpose W. So your solution error function will be like this, and that's the way we solved our, we reached the normal equation. We solved this with differentiating it with respect to W. We end up with this one. The solution will be Z transpose Z plus lambda IW will be equal to Z transpose T. Or when we keep our W on one side, this term goes to the other side. So Z transpose Z plus lambda I inverse. If you replace Z with X, this is normal equation, right? Except you are including identity matrix of identity matrix will be a square matrix where all entries on the ridge of this matrix are 1. All other entries are 0. There will be as many rows as many input variables. So your normal equation is having this term mu. Lambda is your choice for the penalty term. Maybe it can be, if it is 0, that means you don't want to give any penalty. Then this term will be 0. If it is 1, it's going to be ridge regression. The size of the penalty term changes the name. So all terms 0, only the diagonal is non-zero. This diagonal is also called the ridge of the matrix. That's the reason we call this solution ridge regression solution. We take the inverse Z transpose T. So now what we do is that we simulate this situation that we looked at. We create 3 variables, x1, x2, x3, with correlations among them. How? You can use x1 can be a random number, and then x2 you can derive from that random number by multiplying it with some factor, right? And adding them both. And then x3 will be another random number that is independent from x1 and x2, so that you can show that your inputs are correlated in this way. X1 and x2 are highly correlated. Also generate y that is generated from x1 and x2 in high correlation. x3 may be a just random number that has no relationship with y, and then fit your model on this data with the normal equation with ridge regression and see how you can reproduce. Right? So how do we generate x1? You can say if x1 is a random number, random number multiplied by a coefficient. Now this coefficient you keep secret, but you will use it. Maybe it is 1.5, let's say. And x2 is x1 plus noise multiplied by another coefficient that only you know, right? 2.5. Now when you calculate correlation, you will see that y, x1 and x2 are highly correlated. Generate x3 as a random number that has nothing to do with x1, x2 and y, any random. Then plot the correlation, see if you can get similar kind of correlation matrix. After that, you move on to fitting the regression model that violates IID. Fit the regression model with normal equation and with the ridge regression. And that will be your test number 2 of assignment 3. I have some polishing needed for assignment 1.